Welcome back to the deep dive. Today we are taking on something huge. We're going on a fundamental exploration of the laws that govern how living things, how we move, perceive, learn, and even think.
We are. And our source material for this it's massive. It's over 20 years of research that introduces this really radical unifying idea. It's called coordination dynamics, or CD for short.
Right, CD. And this whole field is really trying to answer what the sources called Patty's origins question.
That's it, yeah. It's the core challenge of complexity, isn't it? I mean, how does this incredibly organized, flexible, biological coordination just arise spontaneously?
You're talking about systems with massive degrees of freedom.
Billions of neurons, hundreds of muscles, dozens of joints, and somehow they all manage to work together coherently without some little conductor in our head waving a baton or a rigid set of instructions.
And I think if you look back at the history of movement science, the classical explanations always felt a bit thin.
A bit inadequate, right? You had ideas like fixed motor programs or, simple closed-loop feedback systems.
And they could describe what was happening, sure.
But not why. Not why that order seemed almost inevitable. They couldn't solve that origins question.
So this is where our deep dive today really gets its anchor. We're looking at what is probably the most successful theoretical approach to this whole problem. The Haken, Kelso, Bunz modeling framework. The HKB model.
Exactly. And you can think of this framework as almost like a theoretical Rosetta Stone. It's managed to unify coordination across these just shockingly diverse phenomena.
We're talking from the simple rhythm of tapping your fingers,
to the timing of your speech, to how we form intentions, how we learn a skill, and even how activity organizes itself inside the brain. It's incredibly ambitious.
And the absolute core idea, the nugget that holds all this together, is an idea that was actually borrowed directly from physics.
Right. It comes from Hermann Haken's theory of synergetics, which is essentially the study of what are called non-equilibrium phase transitions.
Okay, that's a mouthful. Let's break that down a bit.
It fundamentally suggests that the brain and the body, they're not like passive computers just running code. They're active. They are pattern-forming, self-organized, dynamical systems. And the real breakthrough is finding these unifying principles that actually go beyond any specific level of analysis.
What do you mean by level of analysis?
I mean, we can find a principle that works for behavior, like your hands moving, but also for brain activity, and maybe even for matter itself. The sources call this the concept of the abstract order parameter isomorphism.
Whoa. So the logic, the mathematical dynamic that governs, say, water boiling and turning into steam.
That same logic might be what governs a switch in your perception or a change in how you're moving.
That's a radical claim, that we're not bound by the specific biology, but by a more abstract dynamic pattern.
It is radical, but it is so powerfully supported by the data. This framework shows how this, enormously complex adaptive behavior can bubble up from just a few simple nonlinear rules that are just inherent to the nature of open, self-organizing systems.
Like us.
Like us.
Okay, let's unpack this. We had to follow the journey. And it starts with something so simple. So every day, just moving your hands, that researchers revealed a fundamental law of nature.
Yeah.
So the gateway, the real,
the
moment the field of coordination dynamics truly clicked into place was this experiment, the bimanual coordination experiment.
Yes.
It sounds almost childishly simple on the surface, but the results were anything but.
Not at all. It's the classic paradigm. You bring subjects into a lab and you ask them to just rhythmically oscillate their index fingers, like they're wagging them from side to side.
Okay.
And while they're doing this, you systematically, slowly increase the speed, the frequency. And that frequency, that speed, acts as what we call the control parameter.
So that's the knob you're turning to push the system?
Exactly, to push it toward a critical tipping point.
And the first thing they noticed, what was it? What was the first startling observation about how our incredibly complex nervous system handles this simple task?
The observation was bistability. Bistability.
Two stable states.
Precisely. At lower, comfortable frequencies, people can only stably produce two specific patterns, and they can do it without any real learning. Their bodies just fall into these patterns. They behave like perfectly coupled oscillators.
What were those two patterns?
The first is the super stable in-phase pattern. That's where the fingers move symmetrically in the same direction, like windshield wipers. That's a 0-degree relative phase.
Okay, I can picture that.
The second one is the anti-phase pattern. The fingers are alternating, moving in opposite directions. That's 180 degrees out of phase. It's also stable, but
Yeah.
a little less robust.
Now, the sources make a huge deal out of this.
Yeah.
They call the fact that a system with billions of degrees of freedom, neurons, muscles, everything, restricts itself to just these two modes an absolutely amazing fact. Why is it so amazing?
Because it shows you that order is inherent. It's built in. The system isn't being explicitly commanded by some program that says do in phase now.
Right.
It spontaneously selects these two stable modes, and it selects them because they represent the most energetically efficient and dynamically stable solutions available to it. If you try to do something else, like a 90-degree pattern, the system just fights you. It wants to relax back to 0 or 180.
So it's like trying to walk on the side of a V-shaped valley. You'll always slide back to the bottom.
That's a perfect analogy. The in-phase and anti-phase patterns are the bottoms of two different valleys.
But the true revelation came when the researchers pushed the system, when they turned up that control parameter, the frequency.
Yes. This is where we see the phase transition.
So what happens?
As you increase the movement frequency past a certain critical threshold, that less stable pattern, the anti-phase one,
Hold on, it just breaks.
it breaks abruptly, spontaneously. And irreversibly, it switches into the highly stable in-phase pattern. It's not a gradual shift, it's a snap. The pattern itself qualitatively changes.
It's like a flock of birds.
Correct.
They're flying in one formation, and then as they speed up, they just, bam, they snap into a new, more efficient formation.
Exactly like that.
Yeah.
It is the signature of self-organization. And notice, you're going from one structured state, anti-phase, to another structured state, in-phase.
That's a crucial distinction. It's not a breakdown into chaos.
No, it's an order-to-order transition, not disorder to order. That's a really fundamental point. And this led to the third critical finding, which is what happens after the switch.
Okay.
This is the idea of hysteresis.
Hysteresis. What does that term mean in this dynamic context?
It's basically a primitive form of dynamic memory. So you've increased the frequency, right? The anti-phase pattern has switched to the in-phase pattern.
Yep.
Now, what happens if you immediately slow back down? You reduce the frequency back to where you started.
I would assume it switches back to anti-phase.
But it doesn't. The system does not spontaneously switch back. It stays locked in that more stable in-phase configuration.
Whoa. So the system remembers the stable state it found, even after the thing that pushed it there. The high frequency's gone.
That's the core interpretation. The path you took matters. The memory isn't written into some specific neural circuit. It's written into the very shape, the topology of the dynamic landscape. A new, deeper valley was formed, and now you're stuck in it.
Okay, so to capture all of this mathematically, the two patterns, the sudden switch, and this memory effect, they needed a special kind of variable.
A collective variable, yes. Not the position of the left finger or the velocity of the right finger. You need something that captures the relationship between them.
And that variable was?
The relative phase. We use the Greek letter phi, the latter variable. This single variable measures the coherent relationship between the moving parts. It becomes the key order parameter for the whole system. When the stability of the order parameter changes, the whole system changes pattern.
Which brings us then to the HKB model itself. How can one, relatively simple equation capture all of this biological complexity?
The model that Haken, Kelso, and Bunz derived it's just elegant. It provides a mathematical description, often using just a single free parameter that you can adjust, that perfectly captures all the fine-grained data from the experiment.
All of it.
The average phase values, the little wiggles of variability, the variance around those phases, and the precise timing of the switch. All of it. The equation is based on the dynamics of coupled nonlinear oscillators.
And it's the specific way they're coupled in the equation that gives it its power.
Absolutely. That specific mathematical form of the HKB coupling is fundamental because it inherently, mathematically, guarantees the properties that are just critical for any living thing to survive and adapt.
Which are?
Multi-stability, having more than one option available, flexibility, the ease of switching between those options, and the ability to undergo transitions between these collective states. It appears to be a universal law of coordination.
It's genuinely stunning that such a simple experiment with wiggling fingers could lead to something that looks like a universal law. But let's get into the theoretical muscle behind this. We mentioned synergetics.
We did.
How does this theory of non-equilibrium phase transitions, really inform our understanding of life?
Synergetics is really the philosophical and the physical bedrock for all of this. What it states is that nature, when it's operating far from thermodynamic equilibrium.
Which means Systems that are constantly exchanging energy and matter with their environment, like us. We're open systems.
Exactly like us. When you have these open systems, they are driven to spontaneously organize themselves into macroscopic patterns. The same core principles of pattern formation are at work across both animate and inanimate nature.
That's a huge unifying claim. Let's make it more tangible. The classic analogy is the Rayleigh-Bénard instability.
It's the best example, really. So imagine you have a thin, shallow layer of fluid, maybe it's oil in a frying pan or a thin soup, and you start to heat it uniformly from below. At first, nothing much happens. Heat is just transferred by simple conduction. The fluid is. It's homogeneous, it's boring. But as you increase that temperature difference, that's your control parameter, you push it past a critical value.
And the system becomes unstable.
The system becomes unstable, and the fluid spontaneously starts to organize itself into these incredibly regular, rolling, convective cells. You get these beautiful hexagonal patterns.
And those cells, those hexagons, that's the macroscopic pattern. That's the order parameter that just emerges out of the system.
Precisely. You have this complex system of billions and billions of microscopic molecules, and all of a sudden it starts behaving like a handful of organized rolling structures. It's a perfect illustration of how high-dimensional complexity gives rise to simpler, lower-dimensional dynamics.
There's that great quote, surface complexity arises out of deep simplicity.
Or the other way around. You see surface simplicity, those few rolling cells emerging from the deep complexity of all those molecules. And the mechanism for that pattern formation is directly analogous to our fingers switching from antiphase to in-phase.
So that simple demonstration from physics basically gives us a roadmap. It tells us what we should expect to see when any complex system, including a biological one, approaches a tipping point.
Exactly. It lets us predict and then go look for these critical phenomena in human behavior. The first one is critical fluctuation.
Fluctuations. So just randomness, noise.
Well, we observed in the finger experiment that the variability, or what we usually dismiss as noise, in that antiphase pattern, it increases dramatically just before the switch happens.
Most of the time in science, we're trying to filter noise out.
Yeah.
Right? We see it as measurement error. But in this dynamic view, fluctuations are actually functional.
They're essential. They are the system's way of exploring its own boundaries. As the system gets closer to instability, that valley of attraction holding the antiphase pattern gets shallower and flatter. So small, random fluctuations, just internal noise in the nervous system, they get amplified. It allows the system to sort of peek over the edge and explore the neighboring dynamic states. Fluctuations become the engine that drives the transition, allowing the system to find the new, more stable pattern.
So fluctuations aren't errors. They're the creative engine of change.
That's a great way to put it. The second key feature is critical slowing down.
Okay, what does that mean?
As the system gets very near that point of instability, it becomes, well, sluggish, lethargic in how it responds to any kind of input or error.
So if you were to, say, nudge the person's hand.
Exactly. If you perturb the system right near that critical frequency, it takes a significantly longer time for the hands to settle back into that antiphase coordination than it would at a lower, more stable frequency. The system's relaxation time just shoots up because it's kind of stuck on this very flat dynamic landscape. It's hesitant. It's waiting to see which way to fall.
Okay, that makes sense. And the third concept is maybe the most important for understanding how the brain deals with that overwhelming complexity we talked about at the start, the slaving principle.
Haken's slaving principle is the elegant solution to the degrees of freedom problem. It asserts that right around these critical points, the behavior of the entire complex system, all the microscopic components, the individual neurons, the muscle fibers, the chemical reactions, all of it is completely governed or slaved by just a few macroscopic collective modes.
The order parameters, like relative phase.
Like relative phase.
So the brain isn't sitting there micromanaging millions of details. It's just controlling the high-level the order parameter, and all the low-level soldiers just fall into formation because of the dynamic constraints of the whole system.
That's it, exactly. It reduces the computational complexity of the whole problem from, millions of dimensions down to maybe 2 or 3. The order parameters emerge from the parts, and then they turn around and dictate the behavior of the very parts that created them. It's a powerful circular causality.
And just to really hammer home this idea of universality, we should probably touch on Turing instabilities.
Yeah, we should. Alan Turing, decades before any of this, proposed that simple reaction diffusion mechanisms could explain spatial pattern formation in biology, what he called morphogenesis.
Morphogenesis.
Yeah.
So the generation of form.
Right. Think about how a totally uniform layer of chemicals can spontaneously produce stripes or spots or spirals.
Like the dappling on a leopard's coat.
Or the whorled structure of leaves on a plant. It's the same idea. It reinforces this concept that whether we're talking about the physical form of a creature or the ongoing function of a creature, the underlying principles are these self-organizing dynamic mechanisms.
All right, let's take this slaving principle and really apply it to some of the most challenging things our bodies do. The source material points to the work of the Russian school, specifically Israel Gelfand.
Yes, Gelfand argued that to control a complex body, the brain must refer to what he called functional groupings, or synergies. It has to, because the sheer number of degrees of freedom is just too overwhelming otherwise.
You just can't control every muscle and joint individually.
Yeah.
It's computationally impossible.
It's intractable. Gelfand recognized that the potential configurations of your joints and muscles are, well, they're virtually infinite. So the only way to move efficiently is to constrain these vast groups of component synergies or coordinative structures to act as a single lower dimensional unit for a specific task.
So how do we prove these synergies actually exist? And more importantly, that they're flexible and not just, fixed motor circuits hardwired in the brain.
This is where researchers came up with the brilliant speech perturbation test.
Okay.
Speech is a perfect test case. It's incredibly fast, it's highly practiced, and it uses components, your lips, jaw, tongue, that all have multiple functions.
So what do they do?
The experiment was simple. They had subjects speaking, and while they were mid-utterance, their jaw was suddenly and unexpectedly perturbed, sometimes blocked completely for a moment.
Now, if speech was controlled by a fixed, pre-programmed script, like a player piano, blocking the jaw should have just destroyed the sound, right?
Yeah.
It would be catastrophic.
It would be garbled nonsense. But the system showed this incredible instantaneous resilience. The jaw, the lips, the tongue. They immediately and spontaneously compensated for that unexpected block.
Ow.
The tongue might drop a little lower, or the lips might push out a little harder, all to preserve the speaker's intended sound. The acoustic goal was preserved.
This reveals the synergy in action.
The functional synergy. It's like that old trick, the pipe block phenomenon. You can put a pipe between your teeth and still manage to speak intelligibly. This compensation proves that the control is organized around a functional goal, producing a certain sound, not a rigid mechanical sequence of muscle firings. The synergy is flexible, it's adaptive, it's online.
And this same kind of dynamic organization scales up to bigger movements. We see it in locomotion and gait transitions.
Absolutely. Think of a horse. It goes from a walk to a trot, or a trot to a gallop.
And those are sudden, spontaneous transitions. A horse doesn't gradually trottish. It's walking, and then it's trotting.
Exactly. They are classic order-to-order transitions. The biomechanical components, the four legs, are the same, but they get reordered into a new stable phase relationship. And the sources note that these happen as what are called symmetry-breaking bifurcations.
So, for instance, why does a trot tend to transition into a pace, but not really the other way around?
Well, this is where you see differential coupling strengths. The stable phase relationship that holds the trot pattern together. It just loses its stability at a certain critical speed. The system has to find a new stable state.
And that new state is the pace.
Right. And the pattern of the pace suggests that the coupling between homologous limb pairs, so the left hind leg and the right hind leg, is stronger. That stronger coupling dictates the new pattern, and it overrides the weaker coupling between, say, a foreleg and a hind leg. The system breaks the existing symmetry of the trot to find a new, more stable, symmetrical configuration for that higher speed.
It's all just falling into the deepest available valley in the dynamic landscape.
What?
But what about coordinating things that aren't simple one-to-one synchronization? I'm thinking of, a drummer playing a complex polyrhythm.
Yes. The challenge of multi-frequency coordination. This is another area where the dynamics really shine. Studies show that we humans are actually quite limited in the rhythmic patterns we can stably perform at the same time with two hands.
We are.
We are strongly attracted to low integer frequency ratios. Things like 1-to-1, 2-to-1, maybe 3-to-2.
Like patting your head and rubbing your stomach.
Sort of, but try to perform a 4-to-3 rhythm or a 5-to-3 rhythm with your two hands. It's incredibly difficult. It rapidly breaks down into one of the simpler ratios.
So why? Why are those specific simple ratios so much more stable for us than others?
This is explained beautifully by a mathematical concept called Arnold tongues.
Arnold tongues, okay.
If you were to map out all the dynamic possibilities of two coupled oscillators onto a two-dimensional parameter space, you'd see these wedge-shaped regions, these are the Arnold tongues, and they represent mode-locked, structurally stable states.
How should I picture that?
Think of it like musical resonance, or hitting a wine glass with just the right frequency to make it sing. Certain frequency ratios, the simple integer ones, naturally resonate with each other. They maintain their stability much more easily across a wider range of speeds or imperfections.
And those are the widest tongues on the map.
Exactly.
Yeah.
The widest tongues, which mean the most structurally stable and attractive regions in the whole dynamic landscape, correspond precisely to those simple, low-frequency ratios we find easy to perform. The very geometry of the dynamics dictates our innate rhythmic ability.
The universe likes simple ratios, and our nervous system just reflects that preference. Okay, let's take this whole framework and apply it to learning, a process we usually think of in terms of, strengthening synapses.
For coordination dynamics, learning is a phase transition. The traditional view, the synaptic view, it kind of sees learning as moving from disorder to order. You're strengthening connections in what is otherwise a passive system. The CD perspective is that the organism is never disordered to begin with. It already has intrinsic organizational tendencies, those valleys, for in-phase and anti-phase movement. So learning isn't creating order from chaos, it's modifying the existing dynamic organization. It's a passage from one organized state to another, an order-to-order transition.
So what does that look like in an experiment? If you teach someone a new, unnatural pattern like that 90-degree phase we mentioned earlier.
Before you start practicing, that 90-degree pattern is highly unstable. The system constantly wants to fall into the 0 or 180-degree valleys. But after practice, the entire attractor layout is qualitatively changed.
How so?
That 90-degree pattern becomes a new, stable, attractive state in the dynamics. Learning is literally the creation of a new valley in the dynamic landscape, a new place where the system naturally wants to settle. This provides a beautiful mechanism for how information, once learned, is stably guaranteed by the coupling between all the component parts.
And researchers even found that there are different routes to learning, and this led to a really counterintuitive result.
They did. They observed two distinct pathways for learning a new pattern. The first was what they called the shift route. This is where your pre-existing stable state, say the in-phase pattern, is gradually, smoothly dragged toward the required new pattern.
The smooth, gradual path.
Right. The second was the bifurcation route. This is where the required pattern is created abruptly as a completely new, stable pattern. It just pops into existence, the snap transition.
And the counterintuitive part was?
The shift route, the gradual, smooth path, was found to be significantly slower than the abrupt bifurcation route.
That seems completely backwards. Why would a gradual approach be slower than a sudden snap?
It's all about the dynamic landscape. On the shift route, the system has to maintain constant effort against its own intrinsic preferences, against those deep, original valleys. It's trying to slowly drag the bottom of the valley across a flat, resistive landscape. You're always fighting your own inertia. The bifurcation route, though, is a moment of instability. The system briefly loses its current footing, and then it snaps abruptly into the new, desired, stable state. It's actually energetically more efficient to destabilize and then reorganize than it is to fight the existing stability bit by bit. It shows why studying the dynamics of the process of learning, not just the final performance outcome, is so critical.
We've laid a really solid foundation for how this dynamic framework applies to movement and learning. But now we have to tackle the biggest divide in all of cognitive science. We have to try dissolving the perception-action divide.
The big one.
The big one. Traditional models are built on this strict linear causality, right? First, perception happens, then some computation happens in the brain. Then action happens. 1, 2, 3.
In coordination dynamics, it radically challenges this view. It argues that these principles are level independent and that cause and effect are multi-level. They're not just links in a linear chain. If you try to analyze a complex coordinated system with those linear links, the whole cause-effect story just breaks down.
You had a great analogy for this earlier.
Yeah, the source material notes that causes in these complex systems are less like the links of a chain and more like the legs of a table.
Legs of a table.
All the legs are necessary. They're interlocked conceptually. If you remove any one leg, the whole structure collapses. It's the same with perception and action. They are functionally interlocked aspects of a single dynamic system, and they are constantly co-evolving, informing each other moment to moment.
We're so used to being able to coordinate our actions that we just ignore the problem.
We do. We take it for granted. It's like how people ignored gravitation before Newton. We have to really step back and see coordination as the absolute miracle it truly is.
So how does this framework achieve that unification?
Yeah.
It's through ideas like affordances and informational variables. This is about how the environment and the organism dynamically fit together.
Right. This ecological perspective from Gibson is incredibly powerful. Let's take the gannet example. The gannet is the seabird that dives into the ocean for fish from great heights. It has to fold its wings at the absolute perfect moment just before it hits the water. Too early, it loses speed. Too late, it breaks its wings. How does it time this so perfectly, regardless of its starting height or its dive velocity?
It must be using some kind of immediate measurement of time to impact.
Exactly. And researchers found that the timing is based on a single optical variable called tau, the Greek letter tau. Tau specifies the time to contact, and it's derived purely from the changing size of the object, the water surface, in its visual field.
So the bird doesn't need to calculate its height, its velocity, the force of gravity.
No, it only needs to perceive this single low-dimensional informational invariant that reliably guides its behavior. It compresses all the high-dimensional complexity of the physical world into one meaningful variable.
We see this in human behavior too. The classic example is the stair climbing example. How do we judge if a stair is climbable or what the optimal riser height is?
It's not just an absolute height in inches. A researcher named Warren showed that a person's judgment of comfortable, efficient climbing is determined by a dimensionless number. We call it P. It's the riser height. R, scaled to the person's own leg length, L.
So P equals R divided by L. The environment is scaled to the dimensions of the organism.
And here's the critical part. The optimal value for P was found to be about 0.26. And that value corresponds precisely to the height that minimizes our metabolic energy expenditure when we climb.
That's incredible.
It shows that affordances, the possibilities for action in the world, they're not fixed properties of objects. They are dynamic relationships. They're subject to stabilities and critical points that emerge from minimizing a biological cost, like energy. If a stair makes that ratio too large or too small, the system becomes dynamically unstable, and we perceive the task as impossible or just uncomfortable.
The functional fit between us and the world is itself a self-organizing dynamic. Okay, let's push this unifying idea all the way into pure cognition. CD argues that a percept, the very act of perceiving something, is itself a dynamic pattern. It should show the same features as motor coordination.
And we can test that. We can test it with things like categorical speech perception. In the classic say-stay experiment, you have listeners hear sounds where an acoustic parameter, the duration of the silent gap after the initial ease sound, is varied step by step.
And what do you find?
Just like the finger-wagging experiment, perception shows these abrupt, discontinuous changes. At one point, it's say, 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 and then suddenly, bam, it's stay. And crucially, it exhibits hysteresis.
So if you vary the gap up until the switch point and then you vary it back down, the perceptual switch doesn't happen at the same place.
It doesn't. The perceptual categories themselves behave like stable dynamic attractors. Stability is an attribute of the very act of perceiving.
The perceptual mechanism isn't a linear filter. It's a pattern-forming system.
Absolutely. And you see this even more clearly with ambiguous figures. Think of the Necker cube or the face vase illusion. Your perception just spontaneously switches back and forth between the two possible interpretations.
And those switches happen in variable intervals, what they call dwell times.
Yes, and those dwell times follow a very specific statistical distribution. It's a distribution consistent with an underlying neural dynamic called intermittency, or sometimes phase wandering. This is a system that's described as twinkling.
Twinkling, what does that mean?
It means that attraction, the stabilizing forces that keep you locked into one percept and repulsion, the forces that are pushing you out of it, they coexist in this incredibly fine balance.
How should I visualize that? That sounds very technical.
Imagine a ball rolling very slowly across the floor of a valley that is extremely wide and extremely shallow. It might settle for a moment, but even the tiniest breeze and internal fluctuation can push it, and because the floor is so flat, it can easily wander over to the next shallow valley. It's a state of being coherently organized, but always, always ready to fall apart and reorganize. This is called the metastable regime.
And why is being in this metastable, twinkling state so important for the mind?
It is the generic mechanism that provides flexibility. It stops the mind from getting permanently stuck in a single fixed state, which would kill learning or adaptation, and it stops the mind from flying apart into total disorder. Metastability is that sweet spot where the system maintains its coherence while always being poised for flexible switching.
And this leads us right to the dynamic brain thesis, the idea that the brain itself is a pattern-forming, self-organized system operating in this critical, metastable regime.
That's the idea. We've seen criticality in behavior, so now we have to go look for criticality in the brain, and that's what they did. Using SQUID or MEG experiments, researchers measured brain activity during those bimanual coordination transitions.
And what did they find?
They found that the brain signals, specifically the magnitude of the signal over the motor cortex, exhibited the exact same dynamic signatures as the overt behavior. They saw critical fluctuations where the variability in the brain signal spiked dramatically, and they saw critical slowing down, a sluggish recovery from perturbation right at the moment of the behavioral switch.
So this confirms that abstract order parameter isomorphism you mentioned at the start.
It's the strongest evidence for it. The dynamic law that governs the behavior of my hands is the exact same dynamic law that governs the collective activity of my neurons.
Self-organization is really operating across all the scales.
It is, and you can push it even further down to the microscale. Studies have shown that even the switching between the open and closed states of individual ion channels in the membranes of neurons, it exhibits patterns of intermittency and fractal scaling that look just like the perceptual switching we see with the Necker cube. It hints that these level-independent principles might truly govern biology all the way from the single channel up to consciousness.
This entire perspective, it seems to fundamentally challenge how neuroscience so often relies on the neural circuit metaphor. The idea of a fixed circuit, a central pattern generator, or CPG, that runs a rigid program.
The CPG metaphor it's useful for very simple reflexive tasks, but it becomes deeply problematic for higher cognition. The findings from CD highlight the brain's overwhelming functional reality, which is defined by two concepts: degeneracy and functional equivalence.
Okay, explain degeneracy.
Degeneracy means that many, many different combinations of components can all produce the exact same outcome. Researchers modeled the rhythmic pyloric network in the lobster's stomatogastric ganglion, and they found that you could get virtually indistinguishable rhythmic network activity, the functional output, from wildly disparate combinations of synaptic strengths and intrinsic neural properties.
Meaning, many different parts lists can all achieve the same function.
Precisely. The functional identity of the system is not achieved through a fixed specific circuit. It's achieved through dynamic self-organization and context-dependent recruitment of parts. The neural circuitry is multifunctional. If one part is damaged, the brain has 10 other ways to get the job done because the functional requirement will just recruit different physical components. That kind of dynamic flexibility is it's fundamentally at odds with the fixed circuit metaphor.
Okay, we have to address the final challenge, the big one. Intentionality and agency. If everything is governed by these self-organizing dynamics, where does our will, our choice, fit into the picture?
Coordination dynamics offers a unified, non-dualistic view. Intentions aren't something magical that exists outside the physics of the system. They are expressed as specific parametric influences. They are information, but that information is written in the language of the very order parameters that characterize the system's spontaneous activity. Your intention modifies the dynamic landscape. It makes one valley, one attractor, deeper or more accessible than another.
So my intention to pick up a cup is a specific input parameter that shifts the stabilities of my arm's dynamics.
That's the idea. And we see the strange consequences of this interplay in what some call the Bohr effect. The story goes that the physicist Niels Bohr observed that in a classic Wild West quick draw competition, the cowboy who tries to draw first always loses.
What's the dynamic interpretation of that?
It suggests that conscious, willful timing, trying to force a movement to happen, can actually interfere with the non-conscious, critical premotor processes, things like the Bereitschafts potential or readiness potential.
That's the slow, negative voltage shift in the brain that we can see precedes a volitional movement by up to a second.
Right. If you try to consciously intervene too early or too forcefully in that process, you disrupt the natural, self-organized progression toward the movement onset. You get in your own way.
The natural dynamics are faster and more efficient than our conscious will can manage.
In many cases, yes. But intention can also enhance stability. There's something called the pre-selection effect. It shows that we have superior memory for a movement when that movement was volitional, when it was our own choice, compared to when we were passively moved or just following a command.
So making a choice makes the memory stronger.
It appears so. Volition is linked to an enhanced stability of the learned pattern. It suggests that the very act of choosing deepens the corresponding dynamic attractor. The choice you make stabilizes your system's dynamic configuration for the future.
This has been a truly monumental exploration. If we have to distill it, the core message we've unpacked is that these incredibly diverse biological functions, from the microscale of an ion channel to the timing of a ganet's dive to the way we learn a new skill, they might all be expressions of the same fundamental nonlinear dynamical laws.
That is the synthesis. Coordination dynamics successfully replaces this idea of rigid, fixed programming with flexible, self-organized pattern formation. And it gives us a mathematically rigorous framework using order parameters and phase transitions that lets us connect concepts across neural, mental, and behavioral levels in a way that, frankly, traditional modular cognitive science never really could.
It's like the laws of physics applied directly to the mind, revealing a profound simplicity that underlies all this biological complexity.
I think so. The final provocative thought for you to carry forward from all this is this. The knowledge that our biological systems operate near this brink of instability, what we call criticality, and in this twinkling regime of meta-stability, it suggests that our entire daily experience, our flexibility, our ability to learn, maybe even our consciousness, it might all stem from a fundamental dynamic balance.
A balance between two opposing forces.
Yes, a balance between the integrating cooperative tendency, the force that makes components work together and establish coherence, and the segregating autonomous tendency, which allows those same components to retain their independence and their functional specialization. The ultimate source of our adaptive creative behavior is not a fixed blueprint. It's this inherent self-organization, always poised, always ready to switch, operating right at that dynamic edge between order and disorder. That's what adaptation lives.